For this one, we're returning to our old friend, the block going down a ramp, but this time we're going to throw in an extra enemy, which is friction, but we'll deal with him. So here's the setup. We've got a 4 kilogram block sitting on a 32-degree ramp with a coefficient of friction of 0.2, and I want to know what's the acceleration on this thing when we let it go. First of all, we know that the block is going to accelerate down the ramp and that it's not going to fly up or down, which means we can define this as the x direction to make things nice and simple and call this the y direction. So that's exactly what I'm going to do. And then I'm going to draw a force diagram using those newly defined axes. To keep things as simple as possible on the force diagram, I'm going to draw all of the forces in the y direction in yellow and forces in the x direction in purple. So in this case, we've got three main forces on the block. We've got a downward force of gravity, which is 40, no surprises. We have a normal force, which points straight out from the ramp at this angle, and that's entirely in our y direction if we define this to be the y. And there's also a force of friction, which opposes the object's motion. So that force of friction is actually going to be up the ramp. The friction is going to cause the block to slide down slower than it would if the ramp were made of ice. So now we've got to do a little bit of tricky stuff to figure all this out. So just like for the last block on a ramp, we've got to break the force of gravity into its x and y components. And in order to do that, I just do some tricks. So we've got 40 times sine of 32 and 40 times cosine of 32. And now we have to make up our minds for which one is which. So what is stronger on a 32-degree ramp, which isn't a very steep ramp? It's less than 45 degrees. Is the block pulling more, is gravity pulling more through the ramp or down the ramp? Well, since this ramp is pretty flat, I would say it's pulling more through the ramp, which means FGY will be the stronger one. So we've successfully broken gravity up into its x and y components, which means we don't really care about the 40 anymore. We're going to use these two different vectors instead because they're pretty much equivalent to what we had before. And now we've got to consider our other forces, the normal force and the force of friction. I'm actually going to go back to a method we used before because I think it'll explain this clearly. I'm going to split this up into a y-x chart. We're not really interested in time a whole lot. In this case, we're just looking for acceleration. And I'm going to throw in the information we know. So I've got the different components of gravity, but we still don't know this normal force and we don't know the force of friction. But we can figure one thing out. Look at the net force in the y direction. Vertically, in this direction, we know that it's not accelerating. So we know that the net force here had better be equal to 0. And if that's true, then the two forces are balanced. The force of gravity in the y direction had better equal the normal force. In fact, let me draw that to help you a little bit. So if you look at the picture on the bottom left, maybe you can kind of see what I'm talking about. After you break gravity down into FGY and FGX, FGY must be equal to the normal force. Those two have to match because the forces are in balance in the y direction. So we get a normal force of 33.9. And you might be wondering, why is that useful? Well, you got to think back to another thing from a previous problem. This block on a ramp with friction is pretty tough. But if you think back, we can also use this piece of information. So after applying that information, I got a force of friction of 6.78. In fact, let me just round that off and call it 6.8. And now we've pretty much got all the forces figured out. We know that the force of friction is going to be 6.8, and the net force in the x direction is simply going to be FGX, how hard gravity is pulling it down the ramp, minus how hard friction is pulling it up the ramp. And we end up with a net force of 14.4 newtons going down the ramp. If you've been paying attention to these videos closely, then you're probably sick of hearing the next step, but it's time for F net equals ma to finish this thing off. So we found that the net force was 14.4, and the mass was 4, which gives us an acceleration of 3.6 meters per second.